Welcome to this presentation. I will introduce Cauchy's principle for discrete time systems. We will give some examples also. In this slide, I will present the Cauchy's principle for function f of z. Draw a closed contour C1. This is the closed contour C1 in z plane. Z plane means imaginary of z versus real of z. Z is a complex number. Draw this contour C1 such that no pole or 0 of f of z lies on C1. They can lie inside C1 or outside C1, but not on C1. Let z zeros and p poles of f of z lie within C1. It is not required that you must do only in clockwise direction, but I will use this convention in this course. I will always evaluate in the clockwise direction. Because Zi is complex, f of Zi is also complex. What is Zi? An arbitrary point. So every point is complex, so f of Zi is also complex. We will plot imaginary of f of z versus real of f of z. We will denote that as C2. You have to remember this terminology. C1 is this contour. The new plot is called contour C2. Here is the C2 that we arrived at. Because C1 is closed, that is wherever we start, we have to conclude there, C2 also will be closed. What is Cauchy's principle? C2 will encircle the origin of the f plane z minus p times in clockwise direction. What are z and p? Z and p are number of zeros and poles of f of z within C1. Remember, this is the number of zeros and poles of f of z, and these are within C1. Don't care about what happens outside, we are talking about what happens inside. What is this f? This is the same f that comes here. So this is the Cauchy's principle for function f of z. So we will show an example here. Let us choose the unit circle for C1. Remember, C1 was arbitrary. Now I have chosen C1 to be the unit circle in the z plane, and f of z is given as z minus 0.5. So don't worry about this star here, don't worry about this x here. F of z equals z minus 0.5, and I substitute z equals exponential j omega. Why do I do that? Because I want to evaluate it on the unit circle, and the unit circle is described by this equation. So when I substitute for z in this, I arrive at this equation. So we know that exponential j omega is a circle of radius 1 centered at 0. In order to plot f of z, that is in order to evaluate f at every point, I need to evaluate this, which means that I have to subtract 0.5 from exponential j omega. That is what I mean by subtract 0.5 from every point on the circle. So it will also be a circle, but shifted to the left by 0.5. We will get this circle. So this point, which is at 1, will get shifted to 0.5. The direction is the same as C1 because the direction is not changed, and with one encirclement of the origin. Notice that it encircles the origin once. It is in agreement with Cauchy's principle because this has 1 0 at z equals 0.5. I should have put a 0 here, but take it as a 0 here. In the second example, we will consider f of z equals 1 over z. So z equals exponential j omega. So f of z is exponential minus j omega when we substitute z equals exponential j omega. Now C2 is the plot of this f, and it is a unit circle in the counterclockwise direction, because here it is plus j omega, here it is minus j omega. Does this agree with Cauchy's principle? The C1 has one pole inside, hence P equals 1, it has no 0, hence Z equals 0. So the number of encirclements n equals Z minus P, which is minus 1. So Cauchy's principle predicts that there will be one counterclockwise encirclement, which is what we have obtained here. Thus it is as expected. I have got some examples here to count the encirclements of the origin. In this example, you can see that n is equal to 2, the origin is encircled twice, it goes once and then second time here. Whereas in this example, there is a clockwise direction once and counterclockwise direction once, they cancel each other, so the number of encirclements is 0. Same thing happens in this example, n is equal to 0. Of course, we could have drawn it here, this line, instead of making it cut this curve, we could have drawn here and there would have been no encirclements, that line would not have been cut. So we conclude that there is no encirclement of the origin here. Here it is encircled twice, here also it is encircled twice, here the number of encirclements is 0. We will make use of this in the next video. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.